Hello, good morning everyone. My name is Alok Ranjan and I am a research fellow at Engineering Product Development Pillar at Singapore University of Technology and Design. In today's talk, I will be sharing some of the work we have been doing on the dielectric reliability of 2D hexagonal boron nitride using conduction AFM. So basically, this work started as an academic exercise because HBN is an very emerging, promising material, and it is suitable for a wide range of new class of both devices as well as the systems. And the second part is that hexagonal boron nitride is considered as a suitable dielectric for graphene nanoelectronics. And in order to do so, we must understand the reliability aspect. And so far, the nature of wear out and breakdown largely remains unknown. So this was the reason we got motivated to explore this field. So here is the outline of the talk, a brief background, then we will go through the results and discussion looking at the noise spectroscopy and the dielectric breakdown of HBN, and finally some summary and the conclusions. So if you look at the semiconductor industry, silicon has been one of the key drivers for the scaling and the advances in the nanoelectronics. So we have seen that we moved all the way from the planar FET to the FinFET to the nanowire transistor, where the size of the transistors are in the atomic scales, just few atoms in length. So this has been largely possible because we have been able to nail down to a very mature material, silicon, and able to use its a good mobility conditions. But looking forward, in order to improve further upon silicon, we must look upon new materials. And this is where sort of 2D materials fits in the picture, because if we look at some of the emerging 2D materials, their carrier mobility is much higher compared to silicon. And for example, a layered material provide much improved electrostatics on the channel. And this is the reason 2D materials are very, very promising for future nanoelectronics application. So other than the application for high-speed transistors, there are many other emerging applications of these 2D materials. For example, wearable and flexible electronics, simply because 2D materials are much more robust, they have much more higher mechanical strength. They can be flexible, they can be bendable, so a lot of sensors around it can be built. Another promising area is the quantum computing, where, for example, even defects in 2D materials like hexagonal boron nitride is being used for quantum sensing and single photon emitter applications. And there are a lot of many other applications, for example, spintronics and many more. So although the field started just with a single 2D material, which was first sort of exfoliated, which is graphene, but the recent work of last say 10 years has advanced this field quite a lot, and it is possible to synthesize a wide range of layered materials with different properties, semi-metals, metals, semiconductors, superconductors, and even insulators. So once we have a family of these 2D materials, they can be integrated to form functional devices, for example, transistors and memory elements with much higher performance compared to the conventional silicon-based materials. With regards to the hexagonal boron nitride, it's very interesting to know its initial uses. In fact, it was not being used as a gate dielectric to start with. Rather, the reason for using hexagonal boron nitride was that it provides an atomically flat substrate, which helps to achieve the high intrinsic carrier mobility of a material. So, for example, some of the initial experiments were done where people were just trying to measure the intrinsic mobility of graphene, and they can see that it can reach as high as 10 to power 6 to 7. And but when the same experiments were done, where now instead of freestanding, when they put conventional oxides like high K or SiO2, so the mobility dropped a lot, so by 3 to 4 orders of magnitude. And in this case, we are not really using the high mobility of sort of the graphene. So when the same experiment was actually replicated, when the graphene is sort of encapsulated both sides with HBN, and people saw that the mobility can be boosted a lot by two orders compared to this HFO2 or SiO2, and this is very close to its intrinsic limit. So that was one of the primary motivation for the usage of the hexagonal boron nitride. So as we have seen before that the conventional dielectrics like high K or even SiO2 is not suitable for graphene. This leads to the degradation of the intrinsic electron mobility. And the recent works have shown that this is largely due to three factors, includes interface traps and the defects, the interfacial roughness between high K and the graphene, and also the lattice mismatch. Combining these three effects leads to the drastic loss of mobility of graphene when put on the conventional dielectrics. So HBN is very promising in this context because it is essentially a van der Waals 2D material, and it can seamlessly integrate with other 2D material. And that is one of the reasons it is being used as a gate dielectric for graphene nanoelectronics. So one introductory slide on the hexagonal boron nitride. It is important to observe that both boron nitride as well as the graphene share the same lattice, which is hexagonal, and the mismatch is minimal, which is around just 1.8%. So this it is also interesting to note that both these hexagonal boron nitride as well as the graphene are basically all these 2D materials. So essentially the layers are going to be connected by sort of van der Waals forces, and there is no sort of chemical bonding present at the interface. So no sort of interfacial defects, and the material is also very stable, both thermally as well as chemically, and it's also has a very high mechanical strength, which makes it suitable for sort of flexible applications. Two of the most common ways of growing HBN include chemical vapor deposition (CVD), and the other is high temperature, high pressure thermal gradient approach. So there are both advantages of each of the method. For example, with CVD HBN, it is possible to grow a large area HBN, for example, even on a wafer scale. However, it has good control, say on the monolayer thickness, but very difficult to get a multi-layer thickness, say on a wafer scale. Again, this CVD sort of suffers from sort of intrinsic defects, for example, atomic defects as well as the process-induced defects, which include grain boundaries as well as the triple points. However, thermal gradients are more suitable, say, for research purposes, because they can be made like into single crystals, and then one can use, say, for example, mechanical exfoliation to create sort of the test structures needed. And the typical size of these crystals are in millimeters, and the good thing about this thermal gradient approach is that the defect density is very low, and this can be very useful for demonstrating the properties or devices based on hexagonal boron nitride. So we have actually investigated both these samples. So for example, in the CVD HBN multi-layer sample, if we took These are some of the TEM images of the HBN which was directly grown on the copper substrate, and we can see that there is inherent thickness variation. So all these images have been acquired from the same sample, and even from that we can see that the number of layers at present at the different location is it's not the same. In addition to that, there is also other reliability issues. For example, in CVD HBN, there are still some missing atoms, or they may be reduced crystallinity as well. However, when we make devices, say for example with exfoliated HBN, it provides a very high crystallinity, and also the thickness is highly uniform, although over just a few microns. In addition to that, when we make devices out of it, for example, with a metal interface, it provides a very stable and high quality interface as well. So in our work, we have used both this multi-layer CVD grown HBN on copper substrate, as well as this single crystal HBN, which is grown by the thermal gradient approach. In our experiment, we are using conduction AFM, which is basically ultra sharp tip, probing the material, and then we are applying a sort of electrical bias and measuring the electrical properties. The good thing about this the AFM experiment is that the forces that we apply with a tip on the surface can be controlled using suitable cantilevers. And also we have also control on the ambient. For example, the experiments in this case have been done both in the ultra high vacuum as well as the ambient conditions. So let us go through some of the results. So the first experiment is related to the defect spectroscopy. The idea is actually that when we have atomic scale defect and with a very localized conduction AFM probe, we are able to directly probe those defects and measure their properties. So this is what is shown in the first figure. So what we are trying to do is we have a defect located. We are probing it with a CFM tip, and when we apply a constant bias, the electron flowing from the tip to the defect is being trapped and retrapped, and this leads to this sort of a random telegraph noise, which is sort of the you can see like two level sort of random telegraph noise, which is due to the single defect present in the sample. When in another context, for example, we can purposely create the defect. For example, in the post-soft breakdown scenario where we apply electrical stress to create the defects, and now you can see that we have multi-level sort of RTN, so at least like 1, 2, 3 sort of levels of RTN, and it means that we have more than one defect modulating the charge transport. And in terms of the power spectral density, one can see that for this two level RTN, we have simple the slope of 2, 1 over F2 noise. However, as the number of defects grows on, it changes close to 1 by F. So in this particular case, we have 1 F over 1.5, which is close to 2 defect modulating the charge transport. This is another example where we see that in real time how the defects are being created. So you can see that to start with, we have essentially a two level RTN, but as the time progresses, we can see that there is sudden jump in the current. It means that we have created the defect, and also the DC levels shift, and we have the number of RTN levels. So if we go and plot this data in a histogram, we can see that at least we have sort of 16 levels of the current, which tells that we have at least created 4 sort of defect. And this can be also understood in terms of its power spectral density. So for example, for phase 1 when we have just 2 defect modulating the charge transport, the noise is 1 over F2, but as the defects are added on locally, we can see that the noise becomes 1 over F noise. So other than the noise spectroscopy, it's very important to look and understand the dielectric breakdown in the hexagonal boron nitride before even it can be used for the the 2D materials. So some of the work has looked at the hard dielectric breakdown. So when I say hard dielectric breakdown, it means the current compliance are much higher, typically more than 10 microamps to milliamps range. And when they what they have is basically in this experiment they have a metal substrate, they have the HBN single crystal, they went with the AFM, applied some electrical stress, and after that they were trying to do the image. So this is an optical micrograph and this is the AFM picture. So you can see that we have in the topography image sort of a hill created, a deep hill created. So whenever the dielectric breakdown happens, especially hard breakdown, people found that there is a very large pit formed in the HBN. So there is a drastic material removal happening, and this can be also seen, for example, in this 8 nanometer HBN, where we have sort of 300 nanometer wide sort of pore being formed at the breakdown spot. So the earlier experiment was done under the hard breakdown condition, but in actual circuit condition, we rarely reach those sort of current levels. So our interest was to look at the soft dielectric breakdown, and when we say soft breakdown, the current remains relatively very low. For example, hundreds of nanoamps, and also the earlier experiment was done in ambient, so we wanted to go and verify what happens when we change the conditions, for example ultra high vacuum. So what we found that when we do these experiments under say for example UHV conditions and under soft breakdown condition, majority of the HBN tested sites do not show any pitting. So we do not see any pitting in the soft breakdown conditions. What I am showing here some of the results where we see obvious some of the pitting. So for example, we do observe that only for some locations there are pits, and the size of the pit also depends on the current compliance that we use. So in our case, when we limit the current compliance to 100 nanoamps, we saw pit of say 3 to 4 nanometer formed. This is sort of a partial pitting. So in our experiment, we also found that the hard breakdown in ultra high vacuum conditions for the CVD HBN always results in sort of a very large pit, as what earlier groups have observed. But since we are working in ultra high vacuum and we were using sort of a frequency modulation imaging mode, the debris formed was huge, and it was simply making the phase lock loop imaging very unstable. So we were unable to do the image of the hard breakdown spot. So instead, what we relied on rather on the adhesion, because since we were in the ultra high vacuum, the surface remains clean for a very reasonably very long periods of time. And we also know that for example adhesion is very characteristic to the two surfaces in contact. So for example, when we have say HBN in contact with the metal, it will be very different compared to say when we have two metals in contact. And that is how we use this approach to quantify the soft breakdown and the hard breakdown using in the conduction AFM. So what here I'm showing that what we are trying to do is we were trying to measure both soft breakdown and the hard breakdown. We go first measure the adhesion between the tip and the HBN surface, then we apply some electrical bias, and this bias causes dielectric breakdown. So depending on the current compliance that we choose, it can be soft breakdown or the hard breakdown. And after that, we again measure the adhesion. So what we see here, the result that okay, so compared to say like the fresh, which is unstressed, and the soft breakdown, yes, the adhesion has changed a bit. But if we compare to say with respect to the hard breakdown, the adhesion was just too huge, and the tip could not be simply like we cannot pull off the tip from the surface for the displacement of say 125 nanometer. And also, especially if we look at the electrical data, it also shows that in the soft breakdown condition, the dielectric is still insulating, although it's a bit slightly degraded. So we have a lot of defects nearby, and you can see that there is increase in conductivity, and there is also increase in the adhesion as well. However, in case of hard breakdown, we can see that the post breakdown resistance is around 10 kiloamps, which is very close to the series protection resistance what we have put. So it shows that in the hard breakdown case, we have sort of formed a metallic contact. So in our case, it was a platinum wire tip. So most likely it's going this under hard breakdown condition, it has removed the copper, it has removed HBN, and now platinum wire is in direct contact with the copper. And therefore the adhesion is huge because two metals in ultra high vacuum conditions are known to form very high adhesive contacts. So we did carry out some statistical analysis to understand more about the pitting in the CVD HBN. And the analysis shows that under soft breakdown conditions, when the current compliance are less than or equal to 100 nanoamps, about 70% of the locations show obvious pitting, and only 30% of the locations there is sort of a partial pitting. However, the situation is very different in hard breakdown condition. When we keep the current compliance, say above 10 microamps, about 90% of the locations show full pitting. So the material HBN is removed as the breakdown happens, and only 10% of the locations show partial pitting. So other than CVD, HBN, we also wanted to understand if this breakdown is intrinsic property of the material itself. So we use sort of a single crystal HBN, which was grown by high pressure, high temperature thermal gradient method. And what we are seeing here, the topography image before and after, and where we have applied an electrical stress using ramp voltage stress, and we keep the current compliance to 100 nanoamps. And what we saw that after electrical stress, there is a pit formed, and the size of the pit is around 3 monolayers. So the pitting seems to be a common to both materials grown by CVD as well as the high pressure, high temperature thermal gradient method. For example, what we also found that when the current compliance is further increased, say 1 microamps, it also starts showing swelling effects. So we do see, for example, these are the 4 breakdown spots on, for example, 4 nanometer HBN subjected to current compliance of 1 microamps. And all of them sort of show swelling at their location, and the swelling is around 1 to 2 nanometer. In many cases, we also find that there is a slight bit of pitting formed as well, in addition to swelling. So we actually did some molecular dynamic simulations with our collaborators, and what we have found that when we do this kind of breakdown, the experiments, the current when sort of is around 1 microamp or sort of higher, the temperature that is being reached at these localized sites is very high, and this can lead to lattice orientation, and therefore this is the reason we are seeing sort of amorphization at these localized sites, and this may lead to swelling as well. Next, we also wanted to understand what is the spatial extent of this breakdown. So for example, when we do sort of say like a breakdown, what is the area being affected, because it will ultimately decide how much integration density of devices we can reach. So what we are trying to do this experiment with the CAFM, that say for example we create a breakdown spot, and then we went, for example, say we increase the distance, say 30 nanometer, did another one, increased and did another one. In this way, we also varied the distance. For example, we have 330 nanometer, 100 nanometer, and 300 nanometer. And the data for 30 nanometer, for example, is shown here. So what we see here, that the first breakdown has a higher voltage compared to all others. So what does it mean? That the extent of the breakdown of the first breakdown site is large enough so that all the subsequent breakdown what we are doing it's in close proximity. So it's definitely more than 30 nanometer. And what we did is we extracted the breakdown voltage, and when we plot for all these 3 separation, we found that, well, for 30 nanometer, you can obviously see that the first breakdown is affecting all subsequent breakdown. But for 300 nanometer, we don't have such effect. For example, we can reasonably see that the spatial it's more or less randomly distributed. So this experiment helped us to understand that the spatial extent of the breakdown can be between 30 to 100 nanometer under the soft breakdown conditions. And this also tells us that the device density that we can reach with HBN, assuming breakdown as a reliability criteria, it can be 10 raised to the power 9 transistor per centimeter square. So finally, we also investigated the breakdown field strength in the high quality hexagonal boron nitride, and we found that the breakdown field strength sort of decreases as the thickness is increased, and this is in accordance with the other conventional high quality materials, for example SiO2. Another aspect, we found that the breakdown field, the values of the breakdown field is also comparable to the industry quality sort of SiO2, which also tells that it's a robust material which can be reliably integrated from the breakdown perspective. And another question we were trying to understand is to look at the statistics of breakdown, because it is very important to achieve a robust statistics before the material can be integrated for any practical application. So what we have data here is the breakdown voltage distributions for different thicknesses. In this case, we have 3 nanometer, 3.5, 4, and 8 nanometer. So what we first observed that the beta value, the slope is very high, and which is as good as like SiO2, and which is telling that there is very slight variation in these materials. So this is unlike the case of CVD grown HBN. So if you do the CVD grown HBN, you will see that the beta values are much lower, and this tells us that the CVD sort of needs further improvement. And another aspect is that the sort of the beta values decreases with thickness. So this is actually in against the percolation model, because in conventional dielectrics, sort of beta usually has a positive correlation with thickness, and this also tells us that it would be a right time to investigate how these crystalline materials and the percolation model are correlated. So finally, this is the summary. What we have seen that HBN is a promising 2D material which can be used as a gate dielectric for graphene nanoelectronics. We have also seen that the conduction AFM has proved to be a very useful tool to study the reliability of HBN at the nanoscale, especially at this initial sort of material growth stage. We have also been able to understand the breakdown mechanism using conduction AFM in HBN, and we see that both swelling and pitting are dominant mechanisms. Finally, we have seen that the breakdown statistics in HBN follows a variable model. However, our initial results do show that there is a weak dependency of variable slope on the thickness, and it needs to be further investigated. With this, I would like to thank all my mentors in Singapore, as well as wonderful collaborators both in Singapore and across the globe for their wonderful support, and I had a privilege to work with all of them. I would also like to thank the funding agencies from SUTD and also MOE Singapore for their support. Finally, I would like to thank Zephyr from Park System for this wonderful opportunity. Thank you very much. Have a good day.